you will not welcome everybody to this term's Strachey Lectures. So as many of you know, these are named after Christopher Strachey, who was the founder of the Programming Research Group in Oxford and an early figure in the theory of computer science. So before I introduce our excellent speaker, I want to thank our sponsors, Oxford Asset Management. They've been sponsoring this series since 2015, enabling us to bring amazing speakers. And any students or researchers who want to meet them, you are encouraged to do that after the talk during the coffee. They have a table down there. So please do that. The way we're going to do it, normally, as you probably know if you've been here before, we have questions after and microphones running around, but I happen to know that Rafi, like me, kind of also is very happy to have questions in the middle, so don't be shy if you feel like asking a question earlier, that's fine. Okay, and then we'll do the usual thing with the mics at the end. Okay, so it's my really, really great pleasure to introduce Rafail Ostrovsky. Oh, no, please not yet. I'll do that. Thank you. It's my great pleasure to introduce Rafail Ostrovsky, who is a distinguished professor of mathematics and computer science at UCLA. And I think many of us in this room know him for his foundational work, both in cryptography in that area and also more broadly in theoretical computer science. But I wanted to tell you some facts about him that you might not know. And so he's also got a huge kind of practical career as well. He's got 16 patents. And he's got a bunches of fellowships, and so I'm just going to name a few of them. So he's a fellow of the ACM and of the IEEE, the American Association for the Advancement of Science, and also for the IACR, which is the International Cryptology Research Organization. I thought I'd select two of his many prizes to tell you about. So he's the recipient of the RSA Prize in 2018, and the citation says that he's awarded the prize for contributions to the theory and new variants of secure multi-party computation. And another really prestigious prize is the 2022 McDowell Award of the IEEE Computer Society. And there, the prize was for visionary contributions to computer security theory and practice, including foreseeing new cloud vulnerabilities and then pioneering corresponding novel solutions. So we're really lucky to have Rafi here, and I'm very glad to introduce him.
Thank you so much, Leslie. It's an honor to be here. And without further ado, let me get started. So, okay. The paradox of privacy is that the value of data is in using it, of course. And data is often private, and the question that I want to discuss with you today is how can you compute on joint data toward a common goal while maintaining privacy. So you have some data, I have some data, and we jointly want to compute on it. But of course, the tension in data sharing is that my data is valuable to me and I don't want to share it, so I want to protect it, I want to silo it, I don't want to show it to anyone, I want to redact it. On the other hand, in order for data to be useful, we want to analyze it, we want to share it, we want to learn from it. So how do we reconcile these two sort of tensions is what this talk is about. And there are many examples, passenger manifest no-fly lists, to hunt for people who shouldn't be on a flight, reproducibility of scientific experiments on private data, genetic analysis without revealing your own DNA, healthcare providers sharing, patient data, longitudinal studies of various forms, social, economic, educational, logistics, fraud detection, private machine learning, fintech applications, you name it. And this leads us to a general question, which is, can we compute privately on data sets. And by data sets, what I mean is really siloed data sets that you and I and other people have, but we are not willing to completely share with each other for a variety of reasons. And so here's an outline of the talk. I'll talk about secure computations very broadly and what it means. Then I'll tell you kind of a high-level alternatives. You know, it's just one of the many techniques. I will tell you about alternative to secure computation. And then we'll sort of get to the main course of this lecture, which is garbled circuits. And then I want to discuss actually two specific examples of the two systems. One is sort of was built almost 10 years ago. One was built just 2 months ago. I want to tell you about the actual systems work on this topic and then finish with a few words of conclusions. So first, it will be sort of a very broad discussion, then fairly technical discussion on garbled circuits. So let's start with secure computation. So secure computations are n players, and they all have some secret inputs. Think of it as the data sets. And they want to compute some function. And if Churchill would be around, it's actually easy to do. We all trust Winston, so we all give our inputs to Winston. Winston computes this function f and just gives the output to everyone. And because he is uncorruptible and completely trusted, well, at least that's what we believe, then basically he is not going to tell anyone else what their private inputs are. He's just going to announce the result. Okay, and so secure multi-party computation says, well, we don't have Winston around, so how can sort of this players talk back and forth and emulate as if Winston was still with us and emulate exactly the same functionality? In other words, we simulate this trusted third party, even though the trusted third party does not exist. Through sending messages back and forth, we want to simulate this ideal functionality, Winston. And you can think of it as a virtual enclave simulated on this dealer, or whatever you want to call it. So players simulate this virtual dealer that doesn't exist. And it also guarantees robustness against collusion, cheating, what have you. Okay, so that's basically the goal of multi-party computation. And multi-party computation is quite successful, where we actually show how to do it and do it efficiently for a variety of these functions. Let's actually concentrate on a two-party case, right? Now there's only two players, Alice and Bob. And again, let's look at just a few examples. Let's start with a very simple example, which is an XOR function, right? So let's say, and by the way, XOR is just bits, right? It's 0 and 1, and XOR is just sum modulo 2. So the two players just want to compute sum modulo 2 of the individual bits. How can they do it? How can Alice and Bob do it? As they just tell each other the inputs. Why is this okay? Well, let's just think of what happens. Winston takes these two bits, exclusive forces together, and gives back to both players. Now that you know the output of the function, which is the sum modulo 2, and I know my own input, of course I know your input. I just subtract my bit from the sum, that's your bit. So this is a case where they can just talk freely. They don't need Winston. One player just tells to the other player, my input is 1, or my input is 0, because the input of the other guy is implied by the sum. Okay, and the only thing we want to say is we want to simulate Winston, which says whatever he says back to all of us is okay. It's everything else that's supposed to be hidden. Okay, so for XOR, they can just tell each other the inputs. There's nothing interesting to do here. What about an AND function? Can they just freely tell the inputs to each other? Depends on the input, exactly. So if I have a 0, can I tell you that I have a 0? No, right? Because maybe the other guy has a 0, and then I should keep mum. And if the other guy has 0, of course, if the other guy has 1, then you can freely tell him, oh, I have a 0. Because if the other guy has 1, it will be deduced that my input is 0. But who speaks first, Alice and Bob? If both of them have 0, they're kind of stuck, because both of them don't want to admit to each other they have 0, in the chance that the other guy also has a 0, and then I don't want to say if my input is a 0 or 1. And right, so that's a really problem with an AND function. And then more generally, what about arbitrary Boolean circuit, right? You have some complicated function, maybe something about the input leaks, but not everything. And now how can they compute it? So, and more generally, we'll discuss it today as well. What about arbitrary programs, written in C++, Java, have recursion, pointer jumping, what have you? How can we do this? Okay. And what I'm going to talk about today is some recent advances on two-party computation. Originally, I was planning to talk also about multi-party, but I realized there is no time. Okay. So before we go there, what are the alternatives, right? So multi-party computation is all about the secure computation that simulates Winston. And what are the alternatives that we have? And I just want to cover it because there are alternatives. So what is the alternative? One is trusted platform module, right? SGX of the world and what have you. This is a piece of trusted hardware, and Intel says, hey, no one can break into it. And why? Even if it sits on my machine, no one can break into it because it's protected by Intel. And so both you and I send our inputs to this Intel, the SGX platform. SGX computes an input and just announce it to everyone. So in other words, it acts as a trusted broker just based on the hardware with a guarantee from Intel or from other places that no one can break inside. Well, that sounds fabulous. But, even 15 days ago, there was an article in the scientific paper from Georgia Tech saying, hey, if you allow to instrument your computer with all sorts of sensors around SGX, you can actually steal the keys. And in fact, it happens again and again pretty much every couple of months. This is messing with the thing, this plundering crypto keys, and then there's another very recent work called battering RAM. In other words, if you're relying on SGX, you don't sleep well at night. But that's one alternative. But, I like to sleep. So, okay. So the other option is so-called AWS clean rooms. So that's a service offered by Amazon. And the idea is that offered for secure collaboration by Amazon, 2 more participants give data to this Amazon clean rooms. And they compute and just give you the result. And of course, we must trust Amazon employees instead of just you and me that they're not going to take a sneak peek and see what's inside. And in addition, these clean rooms have very strong restrictions what can and cannot be computed. I'll give you one example. Those of you who heard about private set intersection, that's a problem where you have an input and I have an input. Like you have a list of names and I have a list of names, and we want to reveal to each other which names are common, and we want to reveal it to each other. This is not something you can currently do with clean rooms because it's not possible, it's forbidden in the clean room kind of semantics to reveal even partial inputs of individual players. So like PSI, private set intersection, is not possible in clean rooms, and there are all sorts of restrictions on purpose that is designed in Amazon clean rooms to make sure that my data doesn't leak to you and your data doesn't leak to me, right? But that's a viable solution. Amazon sells this for good profits, so nothing wrong with it. Okay, but that's an option. And the other option is so-called data lakes, Databricks, or cloud warehouse like Snowflake. So here, it's sort of similar to clean rooms. And they say, hey, give us all your data and trust us. We are secure. We are completely unbreakable. And, I'm paranoid by training. So, but, again, they make a lot of money. Once you give us all your data, we will perform computation for you and just give you answers back. That's what they say. And by the way, we store all our data and run our secure software in a rented cloud, like AWS or Microsoft Azure or Google Cloud. So not only do you have to trust us that our software has not a single bug, but you also have to trust that the cloud that we run to do our computations, because we don't want to run software, is also secure, and their employees also are not going to break it. Which is, now you have to trust two entities, right? Amazon and these cloud providers. Again, these people, Snowflake is a big company making, you know, billions of dollars. So I'm not criticizing, I'm saying those are alternatives. Okay, so, and the last alternative I want to mention is so-called fully homomorphic encryption. So so that's a cryptographic primitives, which says given an encryption of X, public key encryption of X and encryption of Y, you can sort of, without having a decryption key, compute the sum of X and Y and multiplication of X and Y. And now you can sort of do it securely, where Alice creates a public key and secret key for this fully homomorphic encryption, gives a public key to Bob, to the guy with the second input, and Bob converts his computation into a circuit that just does addition and multiplication. It's inefficient, but you can do it with polynomial blowup. And then Bob computes whatever function he wants to do and then gives back the encryption of the answer back, and Alice decrypts. So that's certainly a possibility, and in fact, it's a possibility that many people in US government are excited about. The problem is, works only for circuits, cannot do random access without touching, basically multiplexing, touching every encrypted item, unless you assume so-called indistinguishability obfuscation. And indistinguishability obfuscation takes, you know, trillions of years to compute a single AND gate. So, you know, good luck with that. So currently, it's 2 or 3 orders of magnitude slower even than MPC or 2PC. And like some recent benchmark says 1,000 to 3,000 times slower. And even more expensive if you want malicious security. I wrote some paper on this thing, but it's basically very slow. And by the way, MPC is about 300 to 1,000 times slower than insecure computation, right? So you're getting a hit of 300 to 1,000 for MPC times another, you know, 1,000 to 3,000 if you want to do FHE. And so it's quite expensive. And so among MPC, 2PC, if you want constant number of rounds, the only alternative is so-called garbled circuits, which is the main course. And so let's dive right into it. But those are alternatives that you have even before I get into garbled circuits. Any questions before I get into the main topic of today's talk? Okay, let's proceed. Okay, garbled circuits. So let me start kind of slowly and explain what it is. So garbled circuits involves two players, garbler and evaluator. And what garbler does is he is going to take some, for now, Boolean circuit and assign 2 cryptographic keys for every wire, right? So here's a, you know, the 2 keys for the wire labeled A, 2 keys for wire labeled B, and so on and so forth. Those are original keys associated with every wire. And now what he does is he is going to give one of these keys to evaluator, to Eve, but not tell him whether this key corresponds to a 0 or to a 1. Secretly, of course, what he will do is the 2 keys are kind of secretly labeled as a 0 key and a 1 key. Let's say 0 key is red and green key is white. But when he gives it to evaluator, all these keys look alike. They basically look like keys. And so now what he is going to prepare is a cryptographic gadget, which, so Garbler creates a red and green key for each wire and creates a lock gadget that selectively opens an output key based on a provided 2 input keys. So if this is an AND gate, and by the way, every key is custom made for a specific keyhole. So like one red key is going to, so there's a red key that fits into the left keyhole, but not the right keyhole, and another red key and green key that fits into the right keyhole, but not the left keyhole. And what you do is you basically, out of the 6 keys, you create a combination such that if you stick, you know, a particular combination, so here I guess that green key is a 1 and red keys are 0. So if you have two green keys and you stick it into this locked gadget, you unlock a green key, green output key, and all other combinations of a red and green key unlock the red key, the output red key. And as long as we can implement this gadget, we can sort of have kind of a logic of an AND gate, where if you have two keys, not knowing what they are, you stick it in a gadget, you unlock the gadget, and you get some other key. You have no idea if this key is a 0 or 1. Okay, so that's a basic building block of Yao's Garbled circuit, which Andy Yao almost 40 years ago came up with. And so how, given this gadget, and we'll see a little bit later how you build this gadget, but let's assume we have this gadget, how do you do secure computation? Right? And again, here I'm not assuming cheating, just honest but curious. Later, I don't have time actually to talk about malicious behavior, but let's assume now just honest but curious behavior. So what happens is, oops, I'm going the wrong way. What happens is like this. First of all, so Eve has some inputs to the circuit. Let's say the 3 inputs belong to Eve. And this circuit with this gadget was generated by Garbler. So there's another primitive called oblivious transfer, where if Eve has secret inputs 1, 1, 0, for every pair of keys, it can select secretly one of the two keys to get without disclosing to Garbler which key she is getting. So if her input is 1, 1, 0, she gets the first green key, the second green key, and then the red key. And the Garbler doesn't know for every pair which of the two keys Eve got. Okay. Then also there is some way to create this gadget, these digital locks, such that the right combination unlocks the right key. And now you can do the computation. So for example, suppose you have two red keys for A and B. Of course, evaluator doesn't know, Eve doesn't know that those are 0 keys. It sticks it into the locked box and comes out the key called D on D wire. And again, the evaluator says, okay, it's a key. I don't know what color it is. It's just a key, right? And then I feed this D and C into this XOR box, and comes out some key for E. Right? Again, there is some gadget to feed it into this locked box and get the key for E. And then you get the result. So what is the procedure? Using this oblivious transfer, E's input, evaluator gets her keys that correspond to her input. Eve also gets this material, this cryptographic sort of encryption of these digital locks. And for Garbler's keys, her input, he just hands her one key without any explanation, right? And now evaluator can compute to get the right key. And then if the Garbler also says, oh, by the way, if you got this last key, it's a 0, and if you got this key, it's a 1. And that's a secure computation where all the intermediate keys, the Garbler don't tell to the evaluator what color they are, and therefore the evaluator has no clue whether, it's the intermediate value is a 0 or 1. Okay, so now let's actually dive in and see how we can build this gadget. Okay, so here's an AND gate again. And let's assume that H is a hash function or a random oracle. So what we do is we have two keys for 0, and we have two keys for input wire. In practice, those are AES keys. And by the way, the reason garbled circuits are so efficient is that every Intel chip, or even AMD chips nowadays, have AES accelerator inside on it. So each one of your computers has AES chip, and it takes 33 clock ticks to evaluate this encryption. It's very fast. That's why it's such an efficient technology. So you basically hash, or think of it as a random oracle, A0 and B0, and to exclusivate it with C0 and so on and so forth, all the combinations. And so now if you have, let's say, A1 and B1, well, you apply it here, you get this thing, right? And now if you know how to compute this part, you add it again, and if you add something modulo 2 twice, it disappears, and you get C1 out, right? So that's a way, that's again original Yao's garbled circuit, where this is a way to create a a table of encryptions such that you can decrypt only one row, and decrypting this one row gets you one of the output keys, not knowing which key it is. Of course, to do it properly, you have to scramble the rows, so you don't know, right? If you just write it, 00011011, then just by figuring out which row you decrypt will leak information. We'll talk about it a little bit more, but you have to scramble the row, and as long as the evaluator can decrypt only one entrance of the row, he gets a key and he says, I don't know what value it is, okay? All right, so now, there's another idea to come up with so-called free XOR. So let me tell you this idea. Free XOR is the following idea. Instead of having two keys on the wire, you create, so this is k bits, and delta is also k bits. And what you have is that you have a k bit value for 0, and the same value bitwise exclusive for with delta, which is a global parameter, for 1. And delta you can keep the same throughout the entire execution. The point is the evaluator will never know what the delta is because for every y he sees only one value but not both. So either he sees b plus delta or b. Those are k-bit strings, and k is like 128 bits. So he cannot figure out what delta is. But it's actually quite useful because think of what happens for the XOR gate. Suppose you have A or A plus delta and B plus B plus delta. How do you compute C plus delta? Well, you just XOR these two values. And if you check, the right things cancel out, and you get exactly C plus delta. And therefore, XOR gates, if you represent your digital circuit as AND gates and XOR gates now don't require any communication. I just send you encryptions, these tables of AND bits, and XOR bits you just XOR in a clear, and this gets you the right answer. All right. Another thing you can do, actually, before I go there, another thing you can, okay. Another thing you can do is so-called authenticated sharing. So what happens here is that Garbler keeps this 128-bit string A, and evaluator has this 128-bit A, and this represents a 0. And Garbler keeps an A, and evaluator keeps A plus delta. That means a 1. And Garbler knows the delta, evaluator doesn't know the delta. Okay? And so that's how you encrypt these things. Now, the other thing you can do is there are two additional tricks. One is called row reduction. Row reduction is to say, what if instead of sending a 4 ciphertext, I want to send only 3 ciphertexts? Well, let's make C equal to, C is so far just a random string. Let's actually make it equal to hash of A and B. And therefore, this is 0. Right? Now we just have to send 3 ciphertexts, not 4 ciphertexts. That's great. That was invented here. And then it's an additional idea called point and permute. And that idea is like this. And this is originally for Beaver, Mikali, and Rogova in 1990. We will make the last bit of delta equal to 1. And if you make the last bit of delta equal to 1, basically this A value and A plus delta value, their last bit will toggle. One of them will be 0 and one of them will be 1. Let's assign it colors, right? So the 0, let's say, will be called, orange, and 1 will be called yellow. Have nothing to do with the actual logic of the gate. But now what you can do is you can actually mark every entry like this is an entry. If you have an orange key on the left wire and a red key on the right wire, apply H to this table. And you can just color code for every entry which combination of these colors you can do. And therefore, you don't need to try different entries. You can just decrypt a single entry. So this is so-called point and permute, and it's quite useful. All right. So, good. And now I want to bring the main kind of a point of this discussion. What makes garbled circuits different from fully homomorphic encryption? And those are the three observations that sort of drove the last 10 years of research. One of them is that G can selectively reveal semantic value of any wire. In other words, what he can do is he can say, look, this wire, if it has a point and permute bit 0, it's a 0 or 1. And if this point and permute bit is a 1, it's a 0, whatever it is, right? So he can just selectively decrypt by selecting like the last bit to tell the evaluator what semantic value, what is the actual meaning of this wire. Is it a 0 or 1? This looks quite stupid because we want to hide stuff. But it turns out that this is incredibly powerful, that you can selectively reveal the values in the circuit. You'll see why. The second observation is that the evaluator can evaluate garbled circuits lazily, even if some portion of the circuits are still blocked. And the third observation is sort of a kind of a meta observation. Recall that wire labels are strings of k bits. What if we represent these k bits separately as a fresh wires, so k square bits total, that we can selectively decrypt? In other words, we can have a circuit which operates on these keys, but we can also have like this k keys that talk about a specific key, sort of a meta abstraction. That turns out to be incredibly powerful. Okay, so let me illustrate to you why, selectively decrypting some particular value is useful. This is a so-called half-gate trick. What if the evaluator knows the value on this wire, right? Then it turns out that you can actually send just one ciphertext. Here's an idea. You make the output wire to be hash of the input wire, and you send just one ciphertext, which is this hint. And what happens? Well, if this value is false, if the evaluator knows that he has A and it's false, just hash it, and end of 0, output 0, you already know the output, it's a 0. If you know that this value is true, so the evaluator has H plus delta, then given this hint, you can compute hash of H plus delta, and what are you left with? You add this hash of H plus delta to this hint, that H of A plus delta goes away, you get H of A plus B, and now you also have B, so you add B, and you end up with H of A, right? So with just one ciphertext, you can always compute, basically C plus AB times delta, right? Just by this trick. So that's amazing. And now you can actually do two half gates. What you do, so this is just an abbreviation. This is a secret sharing of bit A, secret sharing of bit B, and secret sharing of bit C. And this is what I already explained. So now what you do, but you say, wait a minute, in the AND gate, you cannot reveal one of the wires. I want to have an AND gate where both wires are hidden. And you sort of you introduce additional random variables, lambda sub A, lambda sub B. You reveal lambda sub A and lambda sub B to the evaluator, right? Just by telling him if it's an orange, if it's a 0, and it's red, it's a 1. And now the point is, what you reveal is blinded by this random value, so it doesn't tell the evaluator anything. But the point is now you can sort of evaluate two half gates twice and multiply this out. You also send separately like a cross term, and everything sort of beautifully cancels out, and you get the end of two wires with just sending two ciphertext. So this is your kind of a new definition of a wire value, and just by sending two ciphertexts, you can do it. All right. So let me now start to random access memory, right? So the picture now looks like this. So far, it's a wires. Wires are sort of fixed in advance. And what if you want to do random access, right? You have a CPU that we simulate as a random circuit, and it wants to read and write into this memory. And the decision which items you read is decided at runtime as you execute the CPU steps. So these CPU steps are modeled as Yau's garbled circuits. But now what happens is you can sort of decrypt and say, hey, I want to read location J. right? Reading location J says, oh, I want to get location J. And now what you want to do is you want to take the value stored in location J and feed it into the next CPU step. What does it mean? Decode at runtime, decrypt at runtime J. I want to read J. And that means that I want to have a value which is stored in this location and somehow translate it to either key A or key A plus delta, because this CPU sort of wants to feed the value stored here into the next CPU step. But the problem is this J is revealed ahead of time, so how can you do it? So what does Garbler knows at compile time when he creates the circuits? It notes the actual bit representation of LN data. It also notes knows that at runtime it will decode some address J and now want to translate it here. So the original paper with one of my PhD students at the time, Steve Lu, was like this. It's a language translation problem. Runtime translate this value W or W plus delta to A. And so what you do, but you don't know what W is at location J. So our original idea was to store the language of this location would be pseudorandom function, think of like AES, of with a secret key of this specific location. And if you do it, you can actually do it using PRF. When you found out J, you evaluate PRF of J exclusive for A, and this allows you to translate the value stored here to a value stored here. Okay, so there are a couple of limitations. One is it's horrendously inefficient. You have to execute PRF circuit, which is like 6,000 AND gates inside every memory read. That's terrible. And the second limitation is have to assume circular security, because the PRF depends on garbling and garbling depends on PRF. So there was quite a bit of work in getting rid of this limitation. The idea is to get a binary tree where every node here is a garbled circuit. And you sort of, the idea is you have this value A that the next step of the CPU wants to read, and you pass it as a function argument to this garbled circuits that talk to other garbled circuits all the way down to the memory location to pass as an argument the encoding of A. Okay? And if you do it right, you can sort of do it. And so you do a bit of work, this sort of works, pass all the way down, and then replenish burnt sort of a circuitry, because you can use the circuitry only once. And then you use oblivious round compiler to compile public read to a private read, whatever that means. You can basically compile, because here the evaluator sees which locations you read. You can sort of compile your program into another program where reading locations still hide which real locations you read. That's a subject for a different talk, but that's basically it. And there was, how much time do I have? 10 minutes. Okay, so I want to get to applications, so maybe I should skip all of this. There is more recent work that gets it even faster, but for the purpose of time, I want to maybe skip all of this because that's quite involved. Let me go to here. So in this paper, we sort of improved the overhead to log square and per read write. Never mind how. And in fact, we actually also showed there is a way to sort of in a very compact way to swap these languages around, to swap keys around. And in fact, in the 2 years ago, we also showed how you can create garbled circuits where kind of a function calls could be commutative. You can either execute, you can first execute some function f and then function g, and with the same circuitry, you can execute it in reverse order. You can first execute g and f or f and g. And it's using tricks called tri-state circuits, but I don't have time to do it. But it sort of speeds things up where this thing is practical. Okay, because I have only 10 minutes, I want to tell you And there's a lot of activity in garbled circuits beyond random access. Conditional branching, malicious security, more than 2 parties, black box use only of cryptographic assumptions, garbling with specific algebraic assumptions. It's a very rapidly moving field, but I want to sort of switch gears now and tell you about applications. Okay, so 2 examples. One example is very simple, is from almost 11 years ago. The idea is like this. Suppose you have your cell phone on which you want to compute some function, and your cell phone is not powerful enough to compute it. What you can do is you can give to Amazon a function f, and if you want to hide the function f, you can actually give a universal function, and a seed s to a pseudorandom generator, which the idea is that from small amount of randomness, you can generate as much randomness as possible. But this f is like, hey, I want to compute this function. And then what you tell to Amazon to do is to garble this function into a huge garbled circuit and hand it over to, say, Microsoft Azure. Microsoft Azure, what you do is you take your secret input x, you garble it, and this is just turning every bit into, one of these 2 keys, and just give these keys to Microsoft Azure, which evaluates this function f, gives you a function back, and you just decrypt. You check for every key if it's a 0 key or 1 key. So how much work is this guy doing? Well, he just hands f, the function that he wants to compute, to one service, and then he gets an encoding, these keys to the other service. They sort of do all the heavy lifting, including all the heavy computation. And then he just gets back the answer, which is a few keys, and he checks the color of these keys, and he gets an answer. So this is a very cheap alternative to FIG, where you can delegate any computation to 2 clouds. And as long as these 2 clouds are not in collusion with each other, this is secure. And what I want to leave the time for is a second application called Secure Agent. It's on ePrint, and it came out only like 2 months ago as a paper. Let me tell you what's going on here, because it's a story actually which I'm excited about. So here's Alice and Bob. They have an X and Y. And typically, the way you run MPC is Alice and Bob rent 2 servers on Amazon. And we assume that Amazon servers, even though we both pay money to Amazon, they're not going to look at our individual accounts. And then you run MPC. There's also kind of a variant of MPC called reactive functionalities. Reactive functionalities means that not only can we compute some function, but after this function is computed, we can keep some secret state, which is not known neither to Alice nor to Bob, right? So it's a secret state. And now we can compute additional functionality which updates sort of its states. And I must stress that this state is not known neither to Alice nor to Bob. Okay. And so what we want, and the motivation was like this. Suppose you want to do AI training, right? So AI training is, right, large language model training on 2 data sets. If those data sets are big, even without security, it takes 2 to 3 days to train your data on the data set. So even if using the most efficient MPC, if you want to do it securely, let's say it's a 300 times slower, you're not going to wait half a year to do your training. So what is the alternative? And the alternative that we came up with is like this. We are going to create an MPC that simulates a virtual browser between Alice and Bob. This virtual browser doesn't exist. It's just simulation using secret sharing. This secret browser is going to first go to a Proton Mail and create an account where neither Alice nor Bob know what is the account name or the password. Then this browser, this virtual browser, is going to create an account on Amazon such that the login credentials, so login name, the password, everything, is not known neither to Alice nor to Bob. It's kind of secret shared between the 2 of them. And then this virtual browser is going to create a VM, virtual machine, which will say, if both of you send me the same instructions and the data, I will compute it and then give you both the results. And we actually showed that this is possible to do. How do you do it? Well, let's say it's Alice who connects to Amazon. So what we do inside this MPC is we actually simulate the virtual browser, including TLS encryption. And so what comes out from this MPC is TLS traffic, which is encrypted as if it's somebody sitting on the outside, that goes, say, from Alice to the Amazon. And because it's TLS encrypted traffic, Alice looks at this traffic that comes out from the MPC and says, I have no idea what's going on. It's just TLS traffic, right? TLS traffic is kind of a traffic between you and your bank, so that an eavesdropper in the middle cannot understand it. So we simulate it inside MPC, the TLS traffic. So what comes out is already TLS encrypted with the keys that are shared between Alice and Bob. So what Alice traffics to Amazon is basically already completely encrypted, you know, with standard TLS traffic. And so even if it tries to intervene, it cannot do it. And so what we created is actually kind of a virtual clean room, but who controls this clean room? You and I, not Amazon. We can run any sets of rules or whatever it is. And because this is done where we first create this VM, virtual VM, where not you and not I know the credentials, we can have this VM room run, let's say, machine learning training in a clear. Because, right, just by, let's say, I upload my data to Amazon, you upload your data to Amazon, we create two links, and then create this tell this virtual machine, hey, look at these two links, do the computation, do the training. That's done in a clear, but because neither you nor me have access to this virtual account, it's basically as if it's done in secure computation. And so here we sort of turned cryptography on its head, and we created out of cryptography this virtual accounts that neither you nor I can access, but jointly we can control. Okay, so conclusions. Protocol for parties not, so features of MPC, protocol for parties to interact to obtain only the output and nothing else. But it's quite powerful, as I have seen, as I have shown you. It doesn't release fast corpus of data like you know, differential privacy. It basically outputs the exact value. Highly controlled release. It simulates virtual enclave or replaces honest broker. No fuzzing or noise, right? It's distinct from other privacy mechanisms like CAN anonymity and differential privacy. I believe there was a talk here about differential privacy, so you guys know all about it. But the point about MPC is that you can combine differential privacy and other techniques with MPC. So those are orthogonal issues, and you can combine them together. And it's a very active research area, both in theory and in practice. The last example is to illustrate that MPC is a great API, because you can run cryptography in general to create this virtual enclaves or virtual accounts where to Amazon it looks like a regular account, but in reality it's controlled by you and me together, where neither of us have an access to it. And there are many startups. It's a rapidly evolving field. And I think I finished on time, so let me stop here and take questions.